All right. Good morning, everyone. Let's get started with our today's lecture on image processing. And as a matter of fact, what we are going to do this week, not just today, but on Thursday as well, has nothing to do with image processing. This is not entirely true. It's not entirely true. Of course, everything we are doing here has to do with image processing. But what we are going to study today and in the next lecture will reveal a much deeper insight into what we have been doing for the last couple of lectures. And it is sort of purely theoretic nature, so I will not use the beamer and there will be no images. What we are going to do is to take a deeper look or develop a deeper understanding of what this Fourier transform really is. So our topic is, let's say, deeper insights into the Fourier transform. Before we begin, let me once again recap what has happened up until now. At the very beginning of our lecture series on image processing, we developed an understanding of what digital images are. We saw that we may understand them as pixel matrices, which is great, which is sort of the canonical, that is the natural form in which digital images are given. And already at the very beginning, I pointed out that at the same time, we may think of digital images as functions. And there are several ways of abstraction we may apply there. We can think of digital images either as discrete functions, that is, functions that are defined only for a subset or at certain discrete coordinates, which is given in the case of digital images, or we may think of them as partial functions. That is a more general point of view, where it's okay, it is defined over the whole, in the case of images, plane of xy coordinates, but not for every xy coordinate. There's actually a value of the function. Some of them are being mapped to some value. In that sense, it's a partial function. And then we very briefly and in a very abstract manner studied the notion of vector spaces. And I pointed out that the kind of vectors you may be used to from your previous studies, let's call them the geometric vectors, because in our context they have a clear geometric interpretation. But basically they are tuples of numbers. When we're talking about vector in this usual sense, we assume that we are talking about tuples of numbers for which we define a certain addition and a certain scalar multiplication. And we require that this operation of addition and multiplication fulfill a couple of axioms. Actually, quite a lot of axioms. And then we saw that not only these vectors we are very much used to obey these axioms, but for instance matrices as well, that matrices form vector spaces. And then I took it yet another step further, where I said functions also do obey these axioms. And in that sense we can think of functions as vectors. And then we again looked at sort of vectors proper when we talked about coordinates and coordinate transformations, and did some linear algebra, some rotation matrices, some transformations of vectors as we know them. And then we began to study transformations of functions. Right? And in the case of the Fourier series, that is when we're talking basically about discrete functions, periodic functions, we already saw that what later became the Fourier transformation somehow does something that we know as computing an inner product. Right? And we then generalized from the case of Fourier series to Fourier transforms and studied the Fourier transforms and their properties. And we met the very important notion of convolution. And I promised you that once we're done with all of this, I will close the loop and get back to this notion of vectors and vector spaces. And this is what we're going to do today and on Thursday. So once more, this has nothing to do with image processing directly, but it provides us with a deeper understanding of what we have been doing. And I am a firm believer in the idea that the more you know about something, the less afraid you have to be to use it. Or the more you know about something, the more confident you can be in using that. And so we will now study a much deeper truth as to what we have been doing. And we will start sort of fairly gently. Oh, and one more thing, I will not ask about these things in the exam. But so what's going to happen this week will not be part of the exam. This is sort of far too far afield from the original topic of this lecture series. But again, we are at a university. This is a master's course, and my job is to at least prepare you, open your minds for the deeper truth out there in the universe. So let's start. And I will start this discussion by pointing out or recalling a couple of properties of sort of ordinary vectors. So, in that sense, what I'm going to do right now are preparatory remarks. We shall begin by studying properties of, say, the usual vectors. That is, let us look at vectors A, B, what else do I need? C, X, and Y. And all of these vectors are supposed to be, for the sake of our discussion, n-dimensional vectors defined over the real numbers. So each of these symbols with the underscore here represents a tuple of n numbers. Right? And one of the things we have already encountered quite frequently throughout this lecture is the notion of an inner product. Inner product. And there are different ways of writing it down. I have been using this notation, this pointy bracket to the left, then the vector x, and then the vector y, pointy bracket to the right. Of course, other ways of denoting this inner product is just x, sort of this dot, y. This is probably a notation you are used to. And yet another way of writing is to say we compute the product between the transposed version of vector x and vector y. So these are three different ways of denoting the idea of computing an inner product. What they all mean in the end is the following. All these three expressions are just a shorthand for this summation. We have a sum that ranges from I equals 1 up to n in our case, and then xi times yi. The important thing is not the way we denote the inner product, but the important thing is that all these different notations are shorthands for this expression. Again, we are talking about n-dimensional vectors. Xi and yi are the ith component of these vectors x and y, and we multiply these ith components together and sum these products where I ranges from 1 up to n. I don't know about you, but for me it is always quite helpful to picture what we are doing, to try to, I don't know, create a mental picture of what this really is. And with regard to creating a mental picture, it is particularly this notation that is helpful, because we can think of this expression as a transposed vector x multiplied to a vector y. I have not said it, but when I write this, I do assume that these vectors are all column vectors. Right? And once I'm writing the transpose of the vector, I do assume that it is now a row vector. Well, and if we have this picture in mind, we can look at this operation and understand it as multiplying this component with this one, then multiplying this component with this one, and so on and so forth. Right? And of course, looking at this expression here, we know that this operation between two vectors, where one of them has been transposed, produces just a number. So the inputs to this function inner product, either dot or this bracket thing here, are two vectors, and the output is a number. Right, so this is supposed to be just one thing. These are n things, and this is one thing. So there you have it. This is ways of writing down the inner product. This is what the inner product really is, and this is how we can picture it. Okay, so there's another thing we can do with two vectors, another product, one that we have not discussed so far, but some of you may have already noted it when we discussed about the fact that the Gaussian is a separable operation or a separable filter mask. But to make a long story short, we just talked about the inner product. Now it's time to talk about the outer product. Or another fancy term is dyadic product between two vectors. And again, there are different ways of writing it down. I'll just present two of them right now, and the third one will come later. So we may take two vectors, x and y, and multiply them. This is another operation of multiplication, another product we can define between two vectors. We may also write it like this, x times y transposed. This is probably the better notation in our case. And what this does is, I cannot use an equation sign right now, equal sign right now, but I have to tell you what it does anyway. This produces an object that's actually a matrix, and it has the following properties that for the ij element of this matrix, I will draw a picture in a second, this is given as the I component of vector x times the j component of vector y. And here is a picture, and in this case, a picture says 1,000 words. Picture. So, well, you know, just as we pictured this with respect to the inner product, we can now sort of turn this picture around. So we have this column vector first, and then we multiply a row vector, and the result of this multiplication is a matrix. And the first element of this matrix is the first element of this vector times the first element of that one. This one is this element times that, and you know, like so on and so forth. So there you have it. This is the outer product between two vectors, whereas the inner product produces a scalar, just a number. The outer product produces a matrix. Just for the fun of it, if we think of these vectors as special instances of some more general objects that are called tensors, we would say that a vector is a first order tensor and a scalar is a zero order tensor. So if we compute the inner product between two first order tensors, we get a zero order tensor, that is, we lower the order. If we compute the outer product of two first order tensors, we get a matrix which is a second order tensor. We increase the order of the tensor, just saying. There is a very crucial property of these matrices. They are of rank 1. That is to say, I just pointed out, note, that if we define a matrix M to be the outer product of two vectors x and y, and of course x and y have to agree in terms of their dimensionality, I always assume that, then the rank of this matrix M is 1. And I just recall this notion of the rank of a matrix, that is, the rank of a matrix is the number of linear independent rows or columns. It's actually, there are, in our case, n rows and n columns. And well, if there are fewer columns that are linear independent than there are rows, then the rank would be the number of linear independent columns. If there are fewer linear independent rows than columns, then the rank would be the number of linear independent rows. Just from the way this outer product is defined, or the matrix that results from the outer product is defined, we see that indeed the rows of this matrix are not linear independent, because every row in this matrix is a multiple of this vector. And so the rank is 1. And before we continue with what we actually want to study today, I will point out yet another fact of these outer products, regarding these outer products between vectors. I'll note it as a proposition. And I'll need a lot of space. Proposition. If we consider the following: multiplication between two vectors and a matrix, so and I'll just write it down, A transpose times matrix M times B, where I assume that this matrix M is in fact the outer product of two vectors. What we are considering here is a matrix applied to a vector, gives us another vector, right? And then we have A transpose times a vector. So this is actually an inner product. It's an inner product in disguise, because the second vector here is not really apparent as a vector at this point, but this is an inner product. And if this matrix is of rank 1, or is the outer product of two vectors, then, and this is the proposition, all of this can also be computed as A transpose times X times Y transposed times B. Now what has happened here? We are given, this is also called a, not really a quadratic form, but we are given the product of a vector times a matrix times a vector, this vector times a vector. This matrix is supposed to be of rank 1, that is, we can write it as the outer product of two vectors. And instead of computing this product like so, we may actually compute it as the inner product of vector A and this vector x times the inner product of vector y and vector v. Again, let's have a look at the picture and then we are good to go. Almost. Here is the picture. So what we are interested in here is this situation, a vector times a matrix, I should say transpose vector times a matrix times a vector. Right. And this matrix of ours is supposed to be an outer product matrix, so we have this transpose vector times a column vector times a transpose vector times a column vector. And well, I now may sort of use parentheses like that, this doesn't matter, and all of this gives us a scalar. This is now immediately clear, but I mean it was clear from this point of view already. We have a vector which is called M, matrix M times V, but it is a vector, and this is an inner product between two vectors, so this gives us a scalar. Here is a picture of this fact. Let me actually prove that to you. This is quickly done. So the picture is there already. This is what we can assume to be given, but I will very briefly compute it. So, and I will introduce a new vector. Here's like proof. Well, proof. I will first introduce a new vector. This vector C is supposed to be this product between M and B, right? So what we're given here is A transpose times C. With this substitution we have, then we can write the ith component of this vector C as the sum over all the j, matrix Mij component, times Bj. Right, no big deal here. But we also said that this matrix M is the outer product of x and y, and I will therefore replace this expression with the corresponding term in x and y. So this is the same as the sum over all the j, xi, yj times bj. And now I want you to note that this xi does not depend on the index of summation j, so we can pull it out of the summation. This is to say xi times the sum over j, yj, bj. Okay, we have now developed an understanding for the ith component of this vector C. Now let's compute the inner product between A and C, because this is what's happening here. And the inner product between A and vector C is, given what we just defined, just the sum over all the I, AI, CI. And now we can plug our newfound knowledge as to the CI into this equation here. So this is the sum over all the I, AI, and then xi sum over all the j, yj, bj, and then we are done, right? Because we may just as well write this summation in terms of this product. So there you have it. This once again, we may think of matrix vector products like this one here in terms of two inner products. And now, quickly remind ourselves about the notion of basis vectors. Basis vectors. I shall call them, for the case of finite dimensional vectors over the reals, as everybody calls them EI. So this is a vector E and I. This I is not the ith component of this vector, but this is indeed now the name of the vector. But this is a shorthand for a vector that looks like 0, 0, then there's a 1, 0, lots of zeros. And this here is the ith component or ith element. Right. So this basis vector EI is a vector of lots of zeros. And then there is a 1 at the ith dimension of this vector, and then lots of zeros again. Now what would happen if we were to compute the outer product between two such basis vectors? So we are interested in this product of EI transposed. What is this? That is our question. Outer product between two such vectors. Well, it will be a matrix. That is something we know for sure. And these two basis vectors EI, or this one basis vector which I want to multiply with itself in the outer product manner, contains lots of zeros. Right? So there will be lots of zeros. I don't know. I do it like this. So the main diagonal of this matrix will look like this. At some point there is a 1. This is when sort of this 1 is multiplied with itself. And every other location in this matrix will have a 0. So it's like lots of zeros. Okay, and now we are really almost there, good to go, to start studying what we want to study. Then what happens? Here is the next question. Here is the next question. What if we were to sum all these outer products? First of all, the result will be a matrix, because every term, each term is a matrix. And they are all of the same size, n by n, so that is okay. That is, we'll get another matrix. And for every I, there will be just one 1 in the matrix, and it will be at the location indicated by the I. So if I equals, make it ranging from 1 up to n, make it like so. So for the first term, we'll have a 1 here and lots of zeros elsewhere. For the second term, where I equals 2, we will have a 1 at the 2, 2 position, and so on and so forth. So this is basically this. Oh, isn't that something? We have uncovered the fact that the unit matrix, which I will write like this, it's very important, not much space here, but the unit matrix will be written using this symbol. We have just uncovered the fact that this matrix that has lots of, all of the diagonal elements are 1s, and everything else is 0, this very special matrix can be understood as a summation over outer products of basis vectors. Okay? And because this is the most important thing we have discussed up until now, I need to point out properties of this thing. So this unit matrix from now on will be called the identity operator, because this is what we're really after. We'll generalize all this identity operator. has the following properties. If we multiply it to a vector x from the left, and I will always assume that they are of appropriate sizes, right? So these are n-dimensional vectors, this is an n by n matrix. Nothing will happen. It will give us the vector. If we were to multiply the transpose of the vector from the left to this unit matrix or identity operator, what will happen? Nothing. It would give us the transpose of the vector. So this thing is sort of, yeah, it's the identity element with respect to matrix vector multiplication. And really crucial thing now regarding these funny vector matrix vector products we have been looking at. If we consider x transposed times matrix 1 times vector y, what do we get? X transposed times y. Okay. All right. Now let's switch gears. All of this should have been known to you, I would hope. Maybe there are some funny discoveries that you were not fully aware of, but it's nothing really special. All of this is good and well, in particular because the objects we have been looking at so far are these kind of vectors we really should be familiar with. But as I said at the beginning, we really want to understand why functions are vectors and what kind of vectors functions are and what that has to do with the Fourier transform. And I will therefore switch notation now, or I will introduce another way of writing down vectors, which for the cases we have been looking at so far is not really giving us much, but it will allow us to talk about functions. And this is called the Dirac notation. Dirac was a very famous English physicist. And he introduced another way of writing vectors. And I'll just write it down. He introduced the idea of cat vectors, which we write like this. And this is supposed to mean this vector, x1, x2, all the way up to some xn. So in a sense, this is just another way of expressing these vectors x we have been talking about. But instead of an underscore, we now have this pointy bracket thing here. And he said, let us consider bra vectors, which he wrote like this, which is supposed to indicate the vector x1, x2, all the way to some xn. So it looks like the transpose of this vector, but in addition, we want to have complex conjugation. Okay, here is a mental step. Up until now, we have been focusing on real valued vectors, and now we take it a step further. You know, those x's can be complex numbers. And this is about the same as what we were talking about when we looked at transposed vectors. The special thing is that we have this complex conjugation. This denotes complex conjugation. Bra and cat. Why would he have rewritten it like that and called it bras and cats? Now, here is the answer, and it is actually well, it's funny, because given everything we have discussed so far, we can now write the inner product between a vector x and the vector x, or like I should call it y, I don't know, doesn't matter. Which so far we have been those vectors writing like this. But given this notation, if I write the inner product between a vector x and the vector y, it looks like this. Right? This is a picture of the way we compute the inner product. This is, in a sense, this is a mathematical notation of the picture I have shown you earlier. And I said we have this transpose vector times this column vector. This is sort of the transpose vector where we have to remind ourselves of the effect of complex conjugation. This is the column vector. And this is called a bra, and this is called a cat, and this is a bra cat. There you have it. And this is the reason, the guy was brilliant. The guy was brilliant. And this is actually the reason, now finally, why I have been writing these inner products like this all the time. Right? I didn't use this vertical rule here, but a comma, but that doesn't make much of a difference. But there you have it. The inner product between a bra and a cat is a bracket. And then what about those outer products? How would they look like? Outer product between two vectors, right? So this is again just another way of writing this, and for the outer products we said we can write them like that. So without much ado, they look like so. And this is not really, this up until now, this is just mumbo jumbo. It's just a different way of writing down these things. With respect to the vectors we are used to, we don't really need that because we are in a sense perfectly happy with what we had so far, but we'll talk about more general vectors in a second. But given these two things, I really want to hit it home. So therefore, or thus, we have that this product between a vector and matrix x, y transpose times b. This thing we studied earlier can now be written as the bra A times the cat x times the bra y times the cat b. And here is the brilliance of Dirac, because I spent a whole whiteboard on discussing that this is the same as the inner product of two vectors times the inner product of two vectors. And now we can actually see it. Just because the guy was clever enough to introduce this notation. So first of all, here we have a matrix, x times y. We recognize this as a matrix. Right? If the bars are on the outer edges, then it is a matrix. So there is a matrix here, a vector times a matrix times a vector. But looking at this, we also see it's a vector times a vector times a vector times a vector. We have it pictorially just in front of us. All right. Now, finally, on to new shores. This was basically all just done to introduce you to this notation, which once again says 1,000 words just by looking at it, right? Because these things are vectors, these are vectors, these are matrices, these are inner products. We can see that now. All right, why would we want to write it like that? And Well, the main reason is that the vectors we are really interested right now, and at this point, are not those vectors we have been discussing so far, but we want to understand as to how far functions are vectors. So we'll study functions as vectors. And we would not have to do this, right? Because just from looking at the actions of what defines a vector space, we can verify that, well, the things we have been told throughout our education, school and universities, which are called functions, those things, the functions we are familiar with, they form vector spaces. Right? Just from looking at the actions. But let's develop a deeper understanding as to why that is. And here is an example. Let me draw a function, I don't know, x, and quickly check this parameters again. I will just define an interval, say starting at a, going to some b. X is supposed to be a real valued number. And I will now, draw a function over this interval. And for reasons of simplicity, I'll start this function at 0 or whatever, so some function. And this is supposed to be the function f of x. And now imagine the following problem, which will hardly ever occur in practice, but you see this function, and it is a function that I chose it such that this is not sine of x, this is not x squared, this is not something we could express in a simple closed form expression. Right? I deliberately chose a function that looks strange, where it really is not apparent that it is, say, sine square x plus 15x raised to the power of 5 something. This is not such a function. And your job is now to communicate this function to a friend of yours, I don't know, somewhere else, not in the room, and you cannot scan or take a picture of this function and then send it, but you have to use your phone and your voice only. Go ahead. What do you do? This is basically impossible. But here is one idea for you. Now, you could say, well, it's basically impossible. But what I could do is, I could sort of sample this function at certain points. All right, I don't know. So now we have 9 sampling points. The starting and the end point, like, supposed to be sampling points as well. And now instead of infinitely many values, right, you just have to report 9 of them in this case. And this 9 was an arbitrary artifact of me just sampling this function. And so we are now talking about a discrete function, right? And to point out that this is a discrete function, I will write it like this. So this is f subscript n of x. Either we think of this as a discrete function or as a partial function, but this is again to your liking. In any case, this is a discrete approximation to this continuous function f of x, which is so difficult that there is no closed form expression, so that you cannot communicate it using your voice and your phone. And now comes a crucial idea. We may, I'll switch back to black because it's more readable. We may understand this discrete function, which over the interval from a to b is basically a collection of 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers as a vector. 9 numbers, we collect them in a tuple. So if we interpret Fn as a vector in, well, in our case, the vector space Rn, those are real numbers. Then, and here is the idea, to make it obvious that we are talking about functions now rather than vectors, I will write it like so. Fn. Right. This is a way of writing vectors I have not used so far. So far I just called them x or y or whatever. And now I'm actually really using the cat notation, which already indicates that I'm reserving that notation for functions. But this is, again, just a shorthand for the vector Fn at x1, Fn at x2, and then in our case Fn at x9, right? Because we have, in this silly example, 9 sampling points. Okay, if this is a vector in a vector space, then what are the basis vectors?
Excuse me?
Yeah.
In this encoding, we lose the arguments, right?
The what?
Domain.
Yeah.
So we sampled x1, x2, and xn.
Yeah.
Using this encoding, we lost them.
I'm about to reintroduce them.
Okay.
I'm about to reintroduce them. Yeah, you are right. You are right. But don't be afraid. It's not really important at this point. Here is how I'm going to reintroduce them. Basis vectors. So he had a very valid point. Looking at this picture, we would know, I don't know, this is 1, 2, 3, 4, the value of x4. Right? Here, it is not really obvious anymore. Okay, so to answer your question, what we can do is to introduce something that is called x1 is a, so the first one is actually the beginning of this interval, right? And then we introduce something called delta x, which is b minus a, in our case divided by 9, right? And then we would say that xi is x1 plus, I don't know, I times delta x, something like this. We don't really need that. But you're right, they are lost, but not necessarily so. Right? But still, let us discuss those things. So basis vectors. If this is a vector, and we say, okay, there must be a basis vector, then if it's in the same space, we should probably use the same notation. So xi, cat xi. What could this be? And I would just say it's this vector, 0, lots of zeros, then there's 1, 1, lots of zeros. And this would be the ith place, which we could turn into a real number using something like that. But we are not really interested in this here. This is, yeah, I probably should have been interested in that. But you are happy with this answer, okay? Yeah, then I'll ignore this. Again, so far, not much has happened, right? This is just, we have started with a continuous function, and we have sampled it, and this sampled function is called f subscript n to indicate that there are n sampling points. And since n is a finite number, we can write this sampled function as a vector, and just to indicate that this is not the kind of vectors we usually are dealing with, but a function, I'll write it like this. But it's a vector, it lives in a vector space. If it lives in a vector space, there should be a set of basis vectors. And I said, well, those basis vectors are basically the basis vectors we are used to. Earlier today, I called them E subscript I, and now it is just sort of a cat xi. But looking at this, these are exactly the basis vectors we have been talking about earlier. Now, for these basis vectors in this form, we you know, given what we know about basis vectors, we know that they satisfy well, the inner product between two such ones, so the bracket xi xj evaluates to delta ij, which is to say they are orthogonal or orthonormal. Right? If I is equal to j, then this is 1. If I is not equal to j, then this is 0. So this is, we're good. And the second thing, this is actually something we discussed earlier, which is of much more importance from the mathematical point of view, if you wish, is that the sum where I ranges from 1 up to n. And now we compute these outer products of xi with itself, then this is supposed to produce the identity operator. And a funny name for this in mathematics is to say that they are complete. Complete. And that is once more to say that if we are talking about an n-dimensional space, we compute the sum over n such outer products gives us the identity operator, and that is to say that the basis vectors are complete. All right. And now we are positioned to take this a step further. First of all, given that we have now introduced basis vectors, we can write this function. We may write this function, this discrete function fn, which is a vector for now, can be written as the linear combination I ranges from 1 up to n. Now the value of the function at xi times basis vector xi. Right? This is again nothing new. This is something we are all used to. If we are given a vector, we can express it in terms of the entries of the vector times corresponding basis direction, and then we have to sum it over all basis directions. Right? What is new here is that the vector looks different than the vectors we are used to, and the entry looks different. But this is just a straightforward extension of what we are all knowing. And let me also, one more time, write down the inner product between two such functions. Inner product, so function fn and function Gn, two functions with the same number of sampling points. This is then just the sum where I ranges from 1 up to n function fn at location xi times function gn at location xi. There should probably complex conjugate this g or f, but our example was with a real valued function, so I'm not, but if I were perfectly correct and perfectly general, one of them would have to be complex conjugated. So, the reason why we have been doing all of this up until now is the following. Now, we will look at the situation where you have a lot of time at your disposal to communicate this function to your friend via the phone. Which is to say, we will let this n become very large. Right? Again, your task is to communicate this funny continuous function to your friend, which is basically impossible. So you sample it at, say, 9 points, or twice as many, 18, or twice as many, 36, whatever. Because the more sample points you have, the better the result will be on the other side of the phone line. Right? The more sample points you communicate of that function, the better the picture your friend will have of what you're talking about. So in the limit, you should actually, bring a lot of time and communicate the whole function. Well, if we do this, let this n grow to infinity, then I'll start with the inner product there. Then this function fn, or this cat fn, becomes this. Right. This is to indicate that there are now, infinitely many sample points. This is now the real function. This is now the function we're talking about. And you are used to talk about functions in terms of these expressions. Right? But throughout our discussion, you will see that this is not entirely correct. Basically, everything you have learned so far is slightly wrong. Now, this here is another way of, it's dangerous to say this because it's not true. This is another way of writing this, where I have to put it in quotation marks and it will become clear in a moment. But again, this here, this thing, is now the whole thing. It is not this thing sampled at 9 places, or at 18 or 36 or whatever, but this is a continuous function. It has infinitely many values between here and here. Right? And this is now a vector that indicates this whole thing, and this is, for the first time ever, we see an infinitely dimensional vector. Right? These things have infinitely many entries, because in the real numbers there's an infinity of infinities here. Now, and whenever we have that these things in a summation become very large, the summation becomes an integral. Okay, and that is to say that the inner product between two such functions now is the integral, say, from a to b f of x g of x dx. Right? This is basically, this here becomes this. What we just discussed, the inner products we are used to, becomes this integral, because we are now sampling this function at infinitely many points. And Well then, let us also look at what would happen if we compute the integral of the function with itself, the inner product of the function with itself. This is then the integral from a to b, well, simply f squared of x dx. All right. Now, we will now have to widen our horizon. Now we have really reached a point where everything we have learned up until now, in our lives maybe, I don't know if you have seen this already, has to be left behind. Because we are now talking about functions which we can understand as infinitely dimensional vectors. And we have to ask the question, what are the basis vectors in this space? Right? And for the discrete vectors, that was fairly simple. So sort of just the discrete basis vectors we are used to, maybe multiplied with some delta x's, whatever, right? But fairly simple. We are now dealing with very special vectors, and the inner products, which up until now in our lives basically have been finite summations, are now integrals. And this raises certain questions as to what this means for the basis vectors in this space. And in that sense, we have now finally reached the point of today's lecture where we will learn something new. Right? All of this up until now was just reminding ourselves about stuff we already knew, and then somewhat generalizing this to like stuff we already knew, generalizing this to new situations, and now we have to learn to live with this new situation. And yeah, I'm not going to give it away right away. I'll keep the joke for later. So, we are now addressing the question, what are the basis vectors in this space? And that is to say, somewhat more gentle question is, how are they normalized? Now, of course, one thing we should require from a pair of two basis vectors is this idea of orthogonality, that if they are not the same, their inner product should be zero. And so we require, this is something we should demand of those basis vectors, that if we compute the inner product of two such basis vectors, and whenever I'm writing this now, x cat x, then and this is something else than f, right? This is now a basis vector. This is like this EI we discussed earlier. If it has an x in it, then it's supposed to be a basis vector in the sense that f of x is this at location x. Right? So we require that if we compute the inner product between x and x prime, that this is 0 if x is not equal x prime. And this prime is not the derivative, it is just another basis vector. So this is a good idea. And the question is, and this is where this gets strange. The question is then, what if x is equal to x prime? Should we then require that in this case x times x prime in a product between these two basis vectors is 1? This would be the natural thing, because this is what we have been doing so far. So far, in all our finite dimensional vector spaces, we said, well, if we are given two basis vectors, we want them to be 0, like the inner product to be 0 if they are different, and we want the inner product to be 1 if they are the same. Now, we are talking about infinite dimensional vectors, and it turns out that this does not work there. And so the answer is no. The answer to this, should we require that the inner product of x and x prime equals 1 if x is equal to x prime? No, we will not require that. No. And I will show you why we should not do that. So the best way to see why not is to try to deduce the correct normalization. Best way to see why not is to deduce correct normalization. This is basically to say what we are going to do now. And we do this by, first, we generalize the completeness relation. And that is to say that we want to have the following. We are now talking about infinite dimensional vectors, and if you remember, this completeness relation was to say that the sum over the outer products of basis vectors gives the identity operator. We are now in a situation where there is no summation anymore, it has to be integration. Right? But we can still require that the integral over these outer products, I don't know, x prime, dx prime, that this gives us the identity operator. Right? I am using x prime instead of x because for the result we'll get, it's funnier this way. But this is, again, it's just, it doesn't matter. I could have written, I don't know, ABC here, it does not matter. This is supposed to be the unit vectors, and I call them x prime, and we have an outer product here. The ket times a bra is a matrix, and we want to integrate over all these matrices, and that's supposed to be the identity operator. So this is something we require, and what I will now do is I will multiply a vector to this equation from the right and another vector to this equation from the left. This is just a matrix. It's a very funny matrix right now because it's a matrix of infinite dimensions. Right? And because it is a matrix of infinite dimensionality, I should not really call it a matrix, I call it an operator. This is why I refer to this thing as the operator. Right? But if you want to, you can still think of it as a very, very, very large matrix. Right? And because it is a matrix, I may just as well multiply vectors from the left and from the right. I'll do that. So, second thing we do, we multiply the cat f, so basically our function from the right, and the bra x, so that is to say a unit vector from the left. And if I do this, I'll do it in a couple of steps. Right? Do we have time? Yes, I guess we're good. So what we had was the integral from a to b x prime times x prime dx prime, and I will now multiply this thing from the left and this one from the right. Can do that. And then for the other side of the equation sign, we would find x. Here is another advantage of the Dirac notation. It's just to say that we are now in the situation we have been looking at earlier, right? We have a vector, a matrix times a vector gives a vector, inner product between two vectors. So this is something we saw earlier. Now in the Dirac notation, can do that. It's no problem here. Note the following, that neither this vector on the left nor this one on the right depends on the variable of integration. So usually we pull them out, now we put them in, right? Just for the fun of it. This is the same as if we were to compute integral from a to b, x times x prime times f dx prime, and again on the right hand side nothing changes. This is x times 1 times f. Okay, but we discussed properties of the identity operator, and in particular we said that if we multiply the identity operator to some vector, nothing changes with respect to this vector. So this here is actually the same as the inner product of x and f. All right? No big deal. And now comes the crucial part where I said everything you have learned so far is wrong. Well, I have to be careful, but what is this? We are talking about a function which we now understand to be an infinite dimensional vector. And here we are computing the inner product of this infinite dimensional vector with a basis vector, x. And for the vectors we are all used to, if we compute inner product of some vector with a basis vector, gives us the component of that vector in the direction of the basis vector. So this here actually is this. Can you see that? And this is why everything you have learned so far is wrong. Because when you said, well, we are talking about the function f of x equals something, now you see that if you were perfectly correct, f of x is of course, and this is, you know what it is, the value of the function f at x. And we have exposed that in terms of, we have this function vector f times the basis vector. And this is exactly the projection of x onto this basis vector, which is the value of the function at x. Right? And the same argument applies for this inner product, right? So I'll say likewise. Now we have sort of discussed it for the product of x and f, but would also hold for this one. So the inner product between basis vector x prime and function f is f at x prime. Right? Okay, let us continue. Because what we have here so far is first we looked at the right-hand side, and discussing the right-hand side uncovered this fact. And now that we discovered that for this part of the equation, it is easy to say that it should also hold for this factor here. Right? But this is to say that we have an integral over x, inner product x prime times f of x prime dx. So in a sense we don't see that yet, but all of this has somewhat simplified, and I will continue. Let me, I don't know, let's call this one 1 here for the sake of giving it a name to get back to it. The third thing we have to discuss, or the third idea we will use in our discussion, is that we will let this inner product x prime x, this thing, this is, I'll make it the other way around, sorry. In our equation 1, there is still this. This is still a part of equation 1, right? And we don't know what that is. This is what we are after. We want to actually know what this is. And I will give it another name. I will give it another name, and I'll say let this inner product xx prime be some, what do I say here, unknown function. Be some unknown function, and just for the fun of it, I will call this function delta of x and x prime. Of course, there's a reason why I'm doing this, but right now I'm just, choosing some name. Delta xx prime. One thing we know about this delta xx prime is the following. Something we have already discussed. Since this function delta of x and x prime is definitely 0 for x is not equal to x prime, we can restrict the integral in 1 to an infinitesimal region, near x. And that is to say, this is just in words what I'm going to write down now. This equation 1 can also be written as the integral from x minus epsilon to x plus epsilon. And instead of this here, I will now introduce this new function delta x prime. And here we have f of x prime, and all of this has to be integrated with respect to x prime. Right. Once again, this thing here did occur in equation 1. But for this thing, we do know that it is 0 whenever x and x prime are not the same. We don't really know what it is if they are the same, but we know that instead of integrating over all the interval, we can sort of focus on some tiny interval around x. Right? Instead of this, we plug in this. And instead of integrating from a to b, we integrate from something very much less than x to something slightly much more than x. And here I have already inserted the other expression for the inner product. And remember that on the right-hand side of this thing, we had uncovered this f of x. Okay, so that was on the right-hand side. Now, I will say it before I write it down. If this epsilon here is really, really, really small, very, very small, then it is fairly reasonable to assume that, you know, we have here like some x minus something really small, x minus epsilon, x plus. This is a very, very tiny, 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 tiny interval around x. And we have f x prime says like f at all these values in this really tiny interval. If this is so small, and this function f is reasonably smooth, then it is a good idea to assume that within this really tiny interval, the function does not really change a lot. That if the function is smooth, then it will not, like from x minus epsilon to there will be no jump in this really, really tiny environment. Right? It will be smooth. Well, if it's really smooth, then everything inside this very small interval around x will basically be this. Right? There will not be a lot of change inside this interval. Right?
So it will be exactly fx in the limit, or?
Yeah, exactly.
So this is not the exact equality.
I'm a physicist now.
Okay.
I'm Dirac, not a mathematician. This is how physicists do it. But okay, so what I'm okay, then you have to give me 5 more minutes. Okay, we'll wrap this up. What I am suggesting here is we are talking about something. Let me magnify this here. So we have something here, and say here is x, right? So here is x, and so this thing here is f at x. This here is f at x, and we are now looking at a very, very tiny interval around x. But inside this interval, this is basically constant. Right? If it's small enough, if it is small enough, if I really make this very, very small, then everything inside this interval will be the same value. Well, then we can say, oh, then it's f of x anyway. Because f of x is this one. If we make the interval small enough, then everything inside of the interval will have the value f of x. Right? If we do this, we can say f of x prime is, we can pull it out. And this is what I'm going to do now. And again, this is argued as a physicist would do. This is, you can make this precise. You can make this precise. But I'm rather not going to make this precise because this is taking us really too far away. Because the result we are about to uncover is again one of the miracles of mathematics. It's one of the more recent miracles compared to all the others we have discussed. So if we were to make this precise, we would need much more than we can handle here. So I'm just saying, right, that in this infinitesimal region, this epsilon is really small, so just something ever so slightly above and below x. In this region, f of x prime can be approximated, and here is where I am imprecise. Right? I could not take this if I was a mathematician, but I can because I'm not. I just try to motivate why we are doing what we're doing. Can be approximated by its value at x prime equals f x. Right? So we assume within this tiny interval, it's all the same anyway. This only works if f is reasonably smooth And again, this is something a mathematician would not accept. They would want proof. I don't care. If we do this, if we approximate f of x prime by f of x, we can pull it out of the integral because then it does not depend on the variable of integration anymore. So it can be approximated and be pulled out of the integral. The integral. And that is to say the equation, I should have given it a number, I just erased, can then be written as f of x times the integral from x minus epsilon to x plus epsilon delta of x prime dx prime, and all of this is on the right hand side, nothing changes, f of x. What does that say? Exactly. There you have it. Right. This is our finding. This is to say that this integral from x minus epsilon to x plus epsilon delta of x and x prime dx prime is 1. Okay, give me 10 more minutes and we're done with this. Okay, this already answers our question about the inner product between two such basis vectors. I have now called it delta, but I can sort of reinsert this inner product between x and x prime. What we have learned is that these basis vectors have to be such that a certain integral evaluates to 1. Not that sort of their inner product directly evaluates to 1 if you were to compute. You have to sort of integrate, which is really special. And the reason why this is special is, again, without discussing all the details, that we are now talking about infinite dimensional vectors, and that things become strange once we talk about something that has to do with infinity. And up until now, I have called this a delta, here this one, that some unknown function. Just from looking at this, we can already deduce, well, probably not, but that this delta is not a function. This has nothing to do, this here is nothing you may have seen so far in your lives. This is not a function, because it has a very crazy property. And we'll briefly look at these properties. And then, when we are doing this, we will re-encounter an old friend of ours. We will encounter a friend we have met earlier. So here are some observations. First of all, and this just what I erased is to say that this delta of x prime cannot be finite at x prime equals x. Otherwise, this could not evaluate to 1. So this is already something strange. It's apparently 0 almost everywhere. And then at some point it has a value that is definitely not 1, but probably infinity. What is this? Not a function as we know it, but something special. Cannot be finite, and I don't write it down. Probably I should. I'll write it down. If it was, because if it was, its integral over an infinitesimal region would also be infinitesimal. would also be infinitesimal, right? We are integrating from x minus epsilon to x plus epsilon. This is a very, very small range, and we want this to be 1, and so this has to be something else than some finite number. And this is to say that this function delta of x and x prime should be infinite in such a way that its integral is unity or is 1, right? And this is what I just erased. Again, this is very special, something you may not have seen so far. And here's the third one, and this one is funny. Since this function delta of x and x prime only depends on the difference, let's say x minus x prime, right? It's just important to know how far x prime is away from x. We also, or henceforth, also write, I will now write this function delta in a different way, namely, so x minus x prime. Okay, now we have learned something, and I need to clean the whiteboard once again. Because this is again so important that it has its own name, and which is to say I have to write down a definition. So, definition. And now I put in quotation marks, function delta x minus x prime with these two properties that delta x minus x prime is 0 if x is not x prime, and integral a to b delta x minus x prime dx prime is 1 over this interval a less equal than x less equal than b. These are the two defining properties of this function. Is called the Dirac delta function. There is the Dirac guy again. The Dirac delta function. Almost done. Give me a second. It is hardly an exaggeration that this is again one of the most fundamental concepts in science today, the existence of this thing, and we have already seen it. Who can tell me where? We've already seen it. Not today. Early on. All of quantum mechanics depends on that we can compute with this thing. But let's see where it comes into play for our purposes. So the Dirac delta function fixes the normalization of our basis vectors. That is to say, we have now uncovered that the inner product between x and x prime is delta x minus x prime. And I have to point out that, note, first of all, this delta x minus x prime is only defined in the context of integration. And its integral, this is what we just sort of saw in those equations I erased. Its integral with a smooth function f of x prime is, on the right hand side we had f of x. So, and we are now nearing the grand finale for today. That is to say, third, sometimes delta x minus x prime is therefore called the sampling function. Because it samples the value of the function f of x prime. I'm using the stupid notation we agreed was stupid. I'm sorry, this is an artifact. At x. And by this I mean that, and let me erase this here. If we compute the following integral, delta x minus x prime times f of x prime dx prime, this gives us f of x. All right? Remember that this was the inner product between x and x prime. This is the inner product between the vector f and the basis vector x prime, and we wrote it like this, and on the right hand side we had that. And that is to say that this function delta, if we compute this integral, pulls out the value f of x of the function f. And now it's your turn.
That's Fourier same from
you say? Exactly! We'll come back to the Fourier transform next time. But what is this? This is a convolution. Right? So this is actually really the same as f of x. I'm writing it in the stupid notation, convolved with, say, delta of x. And that is all for today. Now, let me wrap this up. We are on our way to develop a really deep understanding of the Fourier transformation. And again, this is, I believe that the more you know about something, the less you have to be afraid of using it. We are doing this to understand what the Fourier transformation does. What we have been doing today is remind ourselves of properties of vectors, the kind of vectors we are familiar with, and then we have extended that to functions, which can, like discrete functions, are immediately to be seen as vectors, but continuous functions as well. They are special vectors in the sense that they are infinitely dimensional, which entails certain crazy things with respect to inner products, in particular to the inner product between basis vectors, and we have now fixed that. We have found that the inner product between two infinite dimensional basis vectors is basically this Dirac delta function. And here we see that, this concept of what this Dirac delta function does is something we are used to. The Dirac delta function is, in a sense, just a part of a convolution. And here we are. So this is all for today. Next time we will return to the Fourier transform and see what all of this has to do with Fourier transforms. Are there any questions? Yeah.
You derived all these properties and this final result from the assumption that there is a set of basis functions that are complete in this infinite space. Is it always possible?
Yes, it indeed is. Indeed is. I cannot show that to you. Not. I'm sorry. I can tell you. You don't have to worry. Our argument in this is very sloppy, very sloppy. But I guess this is as deep as we can go. We could make this perfectly precise. No problem there. This is mathematical truth. This is nothing I made up. Right? So physicists were the first to think about this. This is funny. In the history of science, quite often developments in mathematics are triggered by ideas in physics. And the development of quantum mechanics, in a sense, when they began with that, they were discussing in thin air, and 10, 20 years later, the mathematicians told them it's okay, it works, and they were, really happy because it's true. This is what happens with theoretical physics, that they have crazy ideas because they want to describe nature, and they need some language that does not exist yet, so they invent the language, pretend it was okay, work with that, and then 10, 20 years later, mathematicians tell them it's okay, don't worry. This is one of the examples. So we sort of did what the physicists did, and the mathematicians have told us this is okay. Yeah. Any other question? Yeah.
For the definition of the Dirac delta function, for the condition, you write x should between a and b, x or x prime.
X. It was x actually. So you have to. For this thing here, we have some x minus x prime, dx prime. This is supposed to be 1. And we need to look at some interval around x. And I had x minus epsilon and x plus epsilon, but I could call this a and I could call this b. Right? And so then I can say this has to be true for a less or equal than x less or equal than b.
So nothing to do with x prime?
No, x prime is the variable of integration.
Oh, okay.
Right? No, so look, we had this x minus epsilon, x plus epsilon. This is a tiny interval about x. Right? X minus epsilon, x. Instead of x minus, I call it a, and instead of x plus, I call it b. So this x has to be between two numbers. They can be fairly far away, don't care. This has to be 1. This is what defines this function. For our discussion, they were fairly close, right? But the definition could be infinity. Don't care. Has to evaluate to 1. Yeah. Any other questions? Okay, then see you on Thursday.